We have looked at the free particle solution to the Schrodinger's wave equation. The next problem that we are going to discuss is the infinite square well. So here the particle is not free anymore. Instead, it is confined to move inside an infinitely deep potential well. This means that the potential is zero inside this region, all right, between x equal to 0 and x equal to a. So inside this region, the potential is 0, but everywhere else outside this region, the potential is infinite. Okay, so this is the specification for an infinite square well potential. Okay, it's 0 inside. Inside it behaves like a free particle, but it cannot go outside because the potential is infinite. It needs infinite energy to get out of this potential well. Okay, that means that we have got a particle that is confined to this potential well. All right, so a particle in this potential is completely free except at the two ends x equal to 0 and x equal to a, right, where an infinite force prevents it from escaping. Right, so once it reaches this point, it's like there's an infinite force that prevents it from escaping from the potential well. Right, now again, this is an idealized problem. It's one of those toy problems, right, one of the simple problems in quantum mechanics where we can solve the Schrodinger equation easily. We can apply the boundary conditions easily. Okay, and then we'll see some of the peculiarities appearing from the quantum mechanical uh, behavior. Now, an analogous classical model would be a cart on a frictionless horizontal air track with perfectly elastic bumpers. Okay, so it just keeps bouncing back and forth forever. Right, it's perfectly elastic bumpers. It doesn't lose energy anywhere. Right, it just keeps bouncing back and forth forever. Right, so this would be a classical analog of the infinite of a particle which is trapped inside this infinite square well. Right, now obviously this potential is artificial, but it serves as a wonderfully accessible test case. Okay, so we are trying to understand quantum mechanics by looking at this simple example. Now, quantum mechanically, we expect this particle to have only bound state solutions because we are talking about a particle that's bound inside the infinite square well. We also expect that the energy spectrum is going to be discrete. The reason is that it can be seen that the Schrodinger equation, right, it's a partial differential equation. It has solutions, it has non-vanishing solutions only for certain values of E if E is less than 0. Right, so bound state corresponds to E less than 0, the total energy being less than 0. Right. Whereas if you're talking about a free particle, that the energy is greater than 0, and if E is greater than 0, then the particle is free to have any value of energy. In other words, we'll have a non-vanishing solution for any value of energy if E is greater than 0. This is what we saw in the case of a free particle. In the case of a free particle, the total energy is positive, which means that the particle is free, right? And the particle was free to have any value of energy. Whereas if E is less than 0, corresponding to bound state, a particle bound in a potential well, if E is less than 0, then the Schrodinger equation has a non-vanishing solution, a non-zero solution, only corresponding to certain values of energy. Which means that we are not going to find the particle with certain values of energy. We are going to find the particle. If you make a measurement of energy, you are going to find only certain values of energy. All right. So this is why we say that it's going to be a discrete energy spectrum. We shall also see that for the one-dimensional infinite square well, the energy spectrum is actually non-degenerate, okay, which means that corresponding to one energy eigenvalue, there's going to be only one energy eigenfunction. Okay. Now we have already solved part of the problem because we said that the wave function has to be 0 outside the infinite square well. The particle is confined inside this infinite square well, which means that the probability of finding the particle outside of the well is 0. The probability is 0 here, the probability is 0 here. Okay, because we are talking about a particle that is bound inside this infinite square well. The particle simply cannot escape the infinitely high wall, if you like. Okay. So the wave function, if the probability for finding the particle outside is 0, that means that the wave function has to be 0 outside. We need to solve the Schrodinger equation only inside of the infinite square well. Okay. Now again, as we said, inside the infinite square well, the potential is 0 everywhere, right? V of x is 0 inside the infinite square well, right? It's infinite outside, but it's 0 inside, okay? Which means that we are still talking about a free particle bound between these two walls. Okay, so we can write down the Schrodinger equation corresponding to the region inside the well between 0 and a. The Schrodinger equation will be like this: minus h bar square divided by 2m d square psi by dx square plus v of x psi, but v of x is 0, so that term disappears. All right, this is equal to e psi of x, all right, or e psi. Okay. Now we can multiply throughout by minus 2m by h bar square. The time independent Schrodinger equation becomes d square psi by dx square is equal to minus 2me by h bar square psi. We can bring it to this side, so we can write this as d square psi by dx square plus 2me by h bar square psi is equal to 0. Now this 2me by h bar square can be written as k square. That's how we get the equation in this form. So inside the well, the Schrodinger equation has this form: d square psi by dx square plus k square psi is equal to 0. Okay, remember that we are talking about the time independent Schrodinger equation. All right. Now this again is the free particle problem that we have already done. The solution is of this form. It is a prime exponential ikx plus b prime exponential minus ikx, because both exponential ikx and exponential minus ikx will solve this equation, as we saw in the case of a free particle. It's exactly the same equation. Okay. Now we can also write this in this form, right? We can write exponential ikx as cos kx plus I sin kx. Right. Similarly, this exponential minus ikx can be written as cos kx minus I sin kx. Right. So we can combine terms of sin kx and cos kx separately. Right. And the expansion coefficients, the new expansion coefficients as written as a and b. Okay, so the same solution can also be written as psi of x is equal to a sin kx plus b cos kx. All right, so I leave it as an exercise for you to find a and b in terms of a prime and b prime. All right, these are just some complex constants. That's all. Okay. So what you need to do is that you have to write exponential ikx as cos kx plus I sin kx, exponential minus ikx as cos kx minus I sin kx. All right. Then you combine the sin kx terms and cos kx terms. All right. And whatever multiplies these terms, you will see that these are constants. You can reassign them as a and b. Okay. Now we could have written this equation from the beginning, because we know that this, right, this equation says that, let's write it here, d square psi by dx square is equal to minus k square psi of x. Okay, now we already discussed in the last class that the obvious solution is of the form exponential ikx, right? But we can see that sin kx and cos kx would also solve this thing. Right? Because if you take the derivative of sin kx with respect to x once, you will get k cos kx. Right? If you take the derivative once more, you'll get minus k square cos minus k square sin kx. Okay. Similarly, you'll see that psi of x equal to cos kx will also solve this equation, which means that a linear combination of sin kx and cos kx will also be a solution. So general solution is now written as psi of x is equal to a sin kx plus b cos kx. Okay. Now so far our solution looks like the free particle solution, but we are not done yet. Now we have to impose the boundary conditions. Okay. Now we said that the wave function, a physically acceptable wave function, has to be continuous everywhere. It has to be continuous everywhere. All right. Now this imposes a certain boundary condition on the system. For example, here we are talking about an infinitely deep square well with x between 0 and a. Okay. We see that there are three regions. We can call the solution in this region as psi1. The solution in this region would be written as psi2. The solution in this region is psi3. We said that psi1 is 0. Psi3 is also 0 because it's an infinite. The potential is infinite in this region. So the wave function is 0. There is no probability for finding the particle in region 1 and region 3. Okay. In region 2, we said that the solution has the form a sine kx plus b cos kx. Now we have this condition that the wave function has to be continuous everywhere. So if the wave function is 0 here, right, the wave function has to be 0 at the wall also, at x equal to 0 also, right? Now suppose the wave function is 0 here in this region and the wave function is not 0 inside, right? Suppose the wave function is not 0 here. That means that there would be a discontinuity. There would be a discontinuity in the wave function. But the wave function has to be continuous, which means that if the wave function is 0 outside, the value of the wave function has to be 0 at x equal to 0 also. Okay, so the first boundary condition says that psi of 0 has to be equal to 0. In the same way, in the third region, also the wave function is 0. So if this has to be continuous with the wave function inside, that means that the wave function has to be 0 at x equal to a also. Okay, what I mean is that psi 2 has to be 0 at x equal to a. So this psi 2, the wave function in the region 2 has to be 0 at x equal to 0. It has to be 0 at x equal to a. Imposing these boundary conditions will give us the complete result. So let's see how we can impose this. Let's first take the condition psi of 0 equal to 0, the first boundary condition. Okay, so you just substitute x equal to 0 in this solution. It becomes a sine 0 plus b cos 0 has to be equal to 0. Okay, we have just substituted x equal to 0. Sine 0 is 0, cos 0 is 1, so we get the solution b equal to 0. So we have fixed the second what do you say, constant. Okay, so b has to be equal to 0, which means that our solution cannot have this b term, cannot have the second term, and the solution now will be written as psi of x equal to a sine kx. All right. So by applying the first boundary condition, we said that the solution cannot have the second term, and the solution has to be of the form psi of x equal to a sine kx. Right? Now let's apply the second boundary condition, which is psi of a has also to be equal to 0. Okay, because the wave function is continuous, it's 0 here, so it has to be 0 here also. Now applying this boundary condition suggests that a sine ka has to be equal to 0. Okay, this means that k cannot take all values, k can only take those values such that ka, right? Sorry, such that sine ka is equal to 0, such that sine ka equal to 0. Now we know the solution to this. Sine ka will be equal to 0 for ka is equal to n pi. Okay. So a sine ka would be 0 if ka is an integral multiple of pi. We know that sine pi, 2 pi, 3 pi, all these are 0. Okay. Now what does this mean? This means that the physically acceptable wave functions correspond to ka equal to 0. So we don't have a physically acceptable wave function for all values of k. Okay, this means that there is no acceptable wave function, no physically acceptable wave function for any value of k. Okay, only for certain values of k that satisfy this particular condition do we have a physically acceptable wave function. All right, so from here we can see that there are only certain values. We can write this like this, okay, corresponding to n equal to 1, 2, 3, etc. So we can write this like this: kn is equal to n pi divided by a. Right, so we have a physically acceptable solution only for certain values of k, which are denoted by kn. Okay, we'll call this as k1, k2, k3, etc., corresponding to different values for n. All right. So with kn equal to n pi by a, our wave function can now be written as psi n of x. Okay, we are talking about the energy eigenfunction. Psi n of x equal to a sine n pi by a. Right? What is this? This is the value of kn. Right? N pi by a. This is k multiplied by x. So these are the physically acceptable energy eigenfunctions. All right. Now, what about the energy eigenvalues? Okay, we clearly see that the energy eigenvalues are also quantized because we had k square in place of 2me divided by h bar square. This is what we called as k square. If k has if k takes only discrete values, that means E also will take only discrete values. Okay. So we can solve for E from here. E is equal to k square, or we can write this as h bar square k square divided by 2m. Right? But there are only certain discrete allowed values of k which are denoted by kn. This means that the energy values are also discrete, given by En is equal to h bar square kn square divided by 2m. Now we can substitute for Kn, which is given by n pi by a. That would make the energy eigenvalues En is equal to h bar square pi square divided by 2ma square multiplied by n square. Okay, so we see that only certain values of energy are allowed. Only certain discrete values of energy are allowed. Okay, we can have E1 is equal to h bar square pi square divided by 2ma square. E2 would be equal to h bar square pi square divided by 2ma square multiplied by 2 square. Okay, so let's just look at this. We'll have the first possible energy value would be E1 is equal to h bar square pi square divided by 2ma square multiplied by 1 square. What about E2? E2 would be equal to h bar square pi square divided by 2ma square multiplied by 2 square. Alright, you just substitute n equal to 2 in here. So that would be 4. Alright, so the first allowed energy value is h bar square pi square divided by 2ma square. The second allowed energy value is 4h bar square pi square divided by 2ma square. Right, the energy values between these are not allowed. Right, there are no non-vanishing solutions corresponding to energy values between E1 and E2. Now we clearly see the difference between the free particle case and the bound state solution. For the free particles case, the free particle could take any energy value, whereas in this case, the particle which is trapped inside this infinitely deep square well can take only certain values of energy, right? Or in other words, the energy is quantized. So when the system is bound, energy becomes quantized. Okay. So as we said, the energy is quantized, which means that only certain values are permitted. The particle which is bound cannot take any value of energy. It can take only certain values. Okay. Now this is expected from the Schrodinger equation, because we said that if E is less than 0 for a bound state, then there are non-vanishing solutions only for certain values of E, right? Which means that there are allowed physical states only for certain values of the energy, right? Now, this is in sharp contrast. This is so different from classical physics. In classical physics, the energy of a particle is given by E is equal to p square divided by 2m. It can take any value. It doesn't matter whether it's bound or not. It can take any value. Right? In other words, the classical energy evolves continuously. In the quantum mechanical case also, there are cases where the energy can change continuously for a free particle, but once the system is bound, then the particle or the system can take only a discrete set of energies. Okay. So we have already done this. We just substitute b equal to 0 and kn equal to n pi divided by a. We get the wave function. We still have to fix this a, fix this constant a. This constant a can be fixed by normalizing. All right. So we demand that so we said that the particle is confined within this region x equal to 0 and x equal to a. So if you are trying to find the particle, you should be able to find it somewhere in here. It has to be somewhere in here. So the probability of finding the particle somewhere inside this infinite square well has to be equal to 1. In other words, we write the normalization condition, integral 0 to a modulus psi n of x whole square dx has to be equal to 1. All right. So in fact, this has to be minus infinity to infinity. All right. But the wave function is non-zero only in the region 0 to a. All right. So the contribution to the integral from everywhere else is 0. So we can simply write this as integral 0 to a. So we demand this integral is equal to 1. Right. So we take psi n of x as a sine n pi x by a. By demanding this, we can fix the normalization factor a, and we write a is equal to square root of 2 divided by a. Right. So we just integrate this, demand that this is equal to 1. right? And then you can get a equal to square root of 2 divided by a. All right. The details of the calculation are given here. You can go through them. Okay, here we just need to use this relation. We have this relation cos 2x is equal to 1 minus 2 sine square x, which means that if we have something like sine square x, all right, so we can write 2 sine square x is equal to 1 minus cos 2x, or sine square x is equal to 1 minus cos 2x divided by 2. We just use this relation, and then we can rewrite sine square n pi x by a as 1 minus cos 2 n pi x by a divided by 2. Okay, and then the integration is just simple. You can carry it out and you see that a is equal to square root of 2 divided by a. Okay. So finally, we have the normalized energy eigenfunctions, which are given as sin of x equal to square root of 2 by a sin n pi x divided by a, where n can take only values 1, 2, 3, etc. As we said, if n equal to 0, then the wave function is 0 everywhere, which means that there is no solution corresponding to n equal to 0. That's the reason why we take only n equal to 1, 2, 3, etc. Now, these are energy eigenfunctions and these are solutions only to the time-independent Schrodinger equation. Okay. So we have now solved the problem, right? We actually solved the time-independent Schrodinger equation to find the energy and the wave function. We got the eigenvalues and the eigenfunction, right? Problem solved. Now we see that there's an infinite sequence of discrete energy levels, right? Even though the energy values are discrete, there are an infinite sequence of energy levels corresponding to positive integer values of the quantum number, and there's no other restriction on these energy eigenvalues other than that they are discrete. Okay, so you will have an energy value corresponding to any integer value for n. Right? Now, as we said, n equal to 0 gives us an uninteresting result where the wave function is 0 everywhere. Right? So that's why we don't talk about that part. Clearly, the lowest allowed energy, all right, the lowest allowed energy is called the ground state energy. It corresponds to n equal to 1, and the value is h bar square pi square divided by 2ma square. Right? You just substitute n equal to 1 in our expression for the energy eigenvalues. Right? Now this is called the 0-point energy, okay, because there exists no state with 0 energy. So even the lowest energy state has a non-zero energy. All right, so note this point, even the lowest energy state here, all right, or the ground state has a non-zero energy. Right? And clearly there is no wave function, or there is no state, there is no physical state corresponding to 0 energy. And the states corresponding to n equal to 2, 3, 4, etc. These are called excited states. So the ground state corresponds to n equal to 1, and all other states are excited states. And their energies are related to the ground state energy by n square multiplied by E1. Right? Why? Because E1 is given by h bar square pi square divided by 2ma square, and the general expression for En is h bar square pi square divided by 2ma square multiplied by n square. In other words, En can be written as n square multiplied by E1. And also, as we said, none of the energy levels is degenerate, which means that there's only one eigenfunction for each energy level. And also we can show that the wave functions corresponding to different energy levels are orthogonal, which means that we can write integral 0 to a psi m star of x sin of x dx equal to delta mn. One part of this we have already proved. If m equal to n, if m is equal to n, then we already showed that integral 0 to a psi n star of x psi n of x dx equal to 1. This we have already shown. This was just a normalization condition. So the only thing that's left to show is that when m is not equal to n, this integral has to give 0. All right, you can try this with psi m of x is written as a. All right, so this a was square root of 2 by a, and sine m pi x by a, right, and psi n of x is written as square root of 2 by a, sine n pi x divided by a, right? So this is a real function, so taking the complex conjugate has no consequence. You can just multiply these things, and I leave it as an exercise for you to show that if m is not equal to n, this integral would be equal to 0. Okay, which means that you will have to show that integral 0 to a, there's this normalization factor coming from each from psi m star and psi m star and psi n, that would be 2 by a, and here you would have sine m pi x by a multiplied by sine n pi x by a dx equal to 0. This is what you need to show. Okay, now this is easily done. Okay, you just have to make use of the formula. You remember that cos a minus b is cos a cos b plus sin a sin b, and cos a plus b is equal to cos a cos b minus sin a sin b. Right? So from here we can write sin a sin b can be written as 1 by 2 cos a minus b minus cos a plus b. Alright, so when we subtract these things, the first terms will get cancelled and we'll get twice the second term. Alright, which is exactly of this one. So the sine m pi x by a, sine n pi x by a can be written using this. Now each term can be integrated easily. Okay, and you will see that when we integrate a cosine, you'll get a sine. And as a consequence, when you apply the limits, all right, when you apply this limit 0 to a, you will see that it will become 0 unless m is equal to n. All right, and we have already seen that if m is equal to n, then the integral is 1. Right, so I leave it as an exercise for you to complete these steps, right, to prove the orthonormality relation, right, or the orthonormality condition. Okay. Let's look at the time evolution. We know how energy eigenfunctions will evolve with time. We know that psi e of x evolves according to psi e of x multiplied by exponential minus I e t by h bar. Okay, so in this case, we'll just substitute E n is equal to n square E1, which means that psi n of x comma t can be written as, okay, psi n of x comma t can be written as, this is psi n of x exponential minus I e n t by h bar. Okay, or we can write this as psi n of x was equal to square root of 2 divided by a sine n pi x by a, and then we would have this factor exponential minus I e n t by h bar. Right, so this is how the energy eigenfunctions evolve with time. Okay, now again, this is not the most general solution. The most general solution would be a linear combination of these stationary states. Okay, we said that these are called stationary states, and the most general solution is a linear combination of these stationary states. Right, so we can write the most general solution as psi of x comma t is equal to the square root of 2 by a is common, so we can pull it out, and then a sum over all the energy eigenfunctions. Right? So general solution would look like this: n pi x by a, and exponential, we can write this en as en can be written as n square e1. Right? This is something that we saw in the previous slide. En is written as n square e1. Right? So that's how we get the most general solution to the Schrodinger equation. Okay, to the time dependent Schrodinger equation. Okay, so here it's exponential minus I n square. It has to be an e1 there. I n square e1 t by h bar. Okay. Now, how should we modify our results if the potential well is symmetric? What happens if the potential is translated to the left by a distance of a divided by 2 to become symmetric? Okay. So we are asking the following question here. This is our infinite potential well that we discussed. We had an infinitely high wall at x equal to 0 and at x equal to a. So this is not symmetric about x equal to 0. We could make this symmetric by shifting this wall, okay, or shifting this potential towards the left by a by 2. Right? So we push this entire thing towards the left by a by 2. That would look like this. So now we would have the wall at 0 will now shift to x equal to minus a by 2, right? And the wall at a would shift to x equal to a by 2, and 0 would be at the middle. Now this is symmetric about x equal to 0. All right. Now you can think of this as shifting the potential, or we can think of this as shifting our coordinate system. We have just shifted the origin of our coordinate system. Okay. Now we already found the solution for this case. We can use the same solution. We can modify the same solution to describe this situation also. Right? So now we are describing the situation. V of x is infinity for x is x less than minus a by 2. It's infinite for x greater than a by 2. It's 0 in this region when x is between minus a by 2 and plus a by 2. Okay, this is the symmetric potential well. Now if we do this, we expect the energy spectrum to remain unaffected. This is because the Hamiltonian is invariant under spatial translations. The Hamiltonian in this case is invariant under spatial translations. How do we check this? You look at the Hamiltonian. The Hamiltonian was given by minus h bar square divided by 2m d square by dx square. Or in general, this is written as p operator square divided by 2m. Right? You see that there is no v of x part. V of x was equal to 0. So the Hamiltonian for this case is of this form, which means that the Hamiltonian actually commutes with the momentum operator. The Hamiltonian commutes with the momentum operator. And we know that momentum operator is a generator of translations. If the Hamiltonian commutes with the momentum operator, that means that the Hamiltonian does not change under space translations. Okay, which means that space translations is a symmetry of the system. Space translation is a symmetry of the system. Okay, which means that in turn the energy spectrum and all these things have to remain unaffected because the Hamiltonian will not change. The Hamiltonian has not changed under this translation. Okay, and again the energy spectrum will be discrete and non-degenerate as we saw before. Right, these things are not going to change because of this space translation symmetry of this system. Okay. You can think of this situation as shifting the origin of the coordinate system to the right by a distance a by 2, okay, such that the origin now coincides with the middle of the well. Okay, so this would be the passive viewpoint. Right? So this is what's happening. Initially, we can think of this as like this. Initially, we have got the infinite well like this. Okay, we have got 0 potential between x equal to 0 and x equal to a, where a is the width of the potential well. Okay, so this is our x-axis. Now in the second case, in the symmetric potential well, we have potential well with the same width a, all right, but now the origin is at this point. X equal to 0 is at the center of the potential well. It's at the middle of the well, all right, and this end now coincides with minus a by 2, and this end is at x equal to a by 2. Okay, now if we look at these two pictures, all right, what's the difference? You can look at it in the passive viewpoint. In the passive viewpoint, we are changing the origin of the coordinate system. So what we have done is that we have shifted the origin of the coordinate system from this point to this point. All right, so we have shifted the origin of the coordinate system from this point by an amount a by 2. So now the origin is at the middle. Right, the origin of the new coordinate system is at the middle. Okay, nothing else changes. It's just the shifting of the origin of our coordinate system. Right, now what happens to the wave function? What happens to the wave function? We have already calculated the wave function in the first case. We have already obtained the wave function in the first case. Okay, how would they be related? How would the wave functions in these two cases be related? Let's see. All right, suppose we want to find the wave function psi prime at the point minus a by 2. Let's say that we need to find this at minus a by 2, right? Psi prime at minus a by 2. All right. Now, just by looking at this situation, we see that it has to be the wave function psi at point 0, at x equal to 0, right? So we had the wave function psi in this case, right? And at the wave function, sorry, at x equal to 0, we know the wave function. We solved the problem, all right? Now the same physical situation appears here, all right? Only that the wall is now at x equal to minus a by 2. This is just a coordinate, all right? But the physics does not change by changing the coordinate. So what we expect is that the new wave function at minus a by 2 has to be equal to the old wave function at 0, all right, or the old wave function at x equal to 0, all right. Why? Because the physical situation at x equal to 0 in the first case is the same as the physical situation at x equal to minus a by 2, the same physical situation, right? We have got an infinite potential, let's say that in an infinitely high barrier at x equal to 0 in the first case, all right. In this case, we have got an infinitely high barrier at x equal to minus a by 2. Same physical situation at different points. All right. So psi prime of minus a by 2 has to be equal to psi of 0. Let's look at another point. All right. This point would be a by 2. By the same reasoning, here the middle of the potential well is at 0, at x equal to 0. All right. But these are the same physical situations. This means that the new wave function at 0, psi prime at 0, has to be exactly equal to psi at x equal to a by 2 in this case. Let's look at this point also. We can say that initially we had an infinitely high uh, potential barrier at x equal to a. We have the same physical situation now at x equal to a by 2. Right? So we can write psi prime of a by 2 has to be the same as psi of a. Okay, this is just the physical argument. All right, we have just translated the origin of our coordinate system. Now looking at this, we see that we can write, in general, we can write psi prime of x, right, as a function of x. This is in the new coordinate system. Okay, this is equal to, we see that this is psi of x plus a by 2. Let's see this works. Okay, psi prime of minus a by 2 is psi of minus a by 2 plus a by 2, which is psi of 0. So this is correct. Okay, psi prime at the point 0, okay, at the point 0 is psi at the point a by 2. Okay, so it's 0 plus a by 2. So similarly, psi prime at plus a by 2, this point, is equal to psi at this point. So this is psi of a. Right? So we can write psi prime of x equal to psi of x plus a by 2. So the only thing we need to change when we go from the asymmetric potential well to the symmetric potential well is that we have to uh, substitute, or we have to replace x by x plus a by 2. So we take the old solution and replace x by x plus a by 2. That would correspond to the change. Okay. So the new wave function has to be such that the new wave function at x equal to minus a by 2, okay, I'm repeating the argument, the new wave function at x equal to minus a by 2 has to be the same as the old wave function at psi of at x equal to 0, has to be the same as the old wave function at x equal to 0, etc. Right? So in general we write psi prime of x equal to psi of x plus a by 2. Okay, I hope the argument is clear. So all we need to do is to make the substitution. Instead of x, you put x plus a divided by 2. Okay, so the wave function now becomes sine of x equal to square root of 2 by a sine n pi divided by a, and instead of x, we have an x plus a by 2 over here. Right? So we can write this also as follows. We can write this as square root of 2 by a sine. We can take this inside, that becomes n pi x divided by a plus, this is n pi by 2 plus n pi divided by 2. Okay. Now what happens when n equal to 1? This becomes sine n pi x by a plus pi by 2. That would be simply cos n pi x divided by a. All right. The same thing happens for n equal to 3, n equal to 5, n equal to 7, etc. Okay. So for odd integral values of n, we have got sin of x equal to square root of 2 by a cos n pi x divided by a. Okay? And similarly, we can see that for even integral values of n, which is 2, 4, 6, 8, etc., the wave function or the energy eigenfunction can be written as square root of 2 divided by a sin n pi x divided by a. So we can say that the wave functions corresponding to odd quantity numbers are symmetric. Right? This is the one corresponding to odd quantity numbers. This is clearly symmetric because cos of minus x is equal to cos x. This is symmetric. Okay. Similarly, those corresponding to n equal to 2, 4, 6, 8, etc. These are antisymmetric. All right. So in other words, we can say that these two functions have definite parities. These have definite parity. These two wave functions have definite parity. Okay. So this is a parity eigenstate with eigenvalue plus 1, and this would be the parity eigenstate with parity eigenvalue equal to minus 1. All right. So with that, we'll conclude our discussion of the infinite square well. We looked at the asymmetric case first. The solution was simple. All right. And then we applied the boundary conditions to see that the energy eigenvalues are actually quantized. Okay. We also found the wave function. We normalized it. And finally, we wrote down the results corresponding to symmetric potential well, right, or symmetric infinite square well, right. So let's stop at that. Thank you.